Have you ever wondered how quantum concepts could revolutionize the way we categorize knowledge? Today, we delve into the fascinating intersection of quantum mechanics and mathematical theories, particularly exploring their application to a hypothetical Dewey decimal algebraic system, or DDS. Let us start with the concept of category superposition. In mathematics, imagine a book that discusses both physics and philosophy. Traditionally, this book would need to be classified under one primary category. However, in a quantum-inspired system, it could exist in a superposition of both categories, represented mathematically as physics plus philosophy. Here, each category is a vector, symbolizing that the book simultaneously belongs to both fields. This mirrors quantum superposition, where, for instance, an electron can exist in multiple states or locations simultaneously. Such a quantum state defies classical categorization, suggesting that our knowledge, too, could be more interconnected and less compartmentalized than current systems allow. Next, consider the entanglement of subcategories. Using graph theory, we could visualize the relationships between different subcategories as a network, where nodes represent subcategories and edges represent connections. These connections need not be hierarchical, but could reflect a more complex, intertwined relationship, akin to quantum entanglement. Moving to quantum probabilities, we could assign quantum probabilities to categories and subcategories to reflect the inherent uncertainty in classifying knowledge. Imagine a state vector Ci that represents the classification of a topic. The coefficients of this vector could indicate the probabilities of the topic belonging to various categories. This approach is inspired by quantum theory, where the square of the amplitude of a state's wave function probabilities reflects the likelihood of finding a particle in a particular state. Lastly, we explore the quantum entanglement of relationships. Mathematically, we could model the relationships between various categories and subcategories using entanglement operators. These operators would represent the interconnections and dependencies across different areas of knowledge, much like quantum particles that exhibit properties dependent on one another, regardless of the distance separating them. This phenomenon is evident in quantum teleportation and quantum communication, suggesting a model where knowledge elements can influence one another across traditional boundaries. In conclusion, quantum mechanics does not just challenge our understanding of the physical world, it also offers a revolutionary perspective on how we might organize and classify knowledge. By applying concepts of superposition, entanglement, and quantum probabilities, we can envisage a Dewey decimal algebraic system that is more adaptive, interrelated, and reflective of the true nature of knowledge, a fluid, interconnected web rather than a fixed, compartmentalized library. This quantum-inspired approach to categorization could ultimately lead to a more holistic and nuanced understanding of the world around us.